Okay, we have here another interesting integral on the board. We've got the integral from 0 to 2 pi cosine cubed x dx. And what I actually wanted to do on this was an alternative method. I don't necessarily think this is a good way to do it or a fast way. I just kind of wanted to explore the alternative method. And so what I wanted to do is just look at this using the complex definition for cosine. So we have here on the board the complex definition for cosine, and this is easily derived from Euler's formula. If you're not familiar with Euler's formula, it just says e to the ix is equal to cosine x plus I sine x. So given this definition here, let's just look what happens if we have cosine cubed of x. So when we cube this out, we can take this out as a 1/2, and we cube 1/2, and we're going to have 1/8 in front. And for this, you can just use like the binomial coefficients or just multiply it out or memorize the formula. But what we're going to have is e to the 3ix plus 3eix plus 3e negative ix. And the last term, again, this is like our cube term, so this is going to be e to the minus 3ix. So now that we have a complex expression for cosine cubed, let's just put this back in the integral and continue. Okay, now we have our updated integral here. Now I brought the 1/8 that we have here out front of the integral. And because this expression isn't too bad, we can just integrate this now and evaluate it and finish it off. But I don't really want to do that, because what I was thinking about is, we have here cosine cubed, but what if this was cosine to the 11th or cosine to the 2023, like a problem I did recently? Well, if we had 2,000 terms, then I really wouldn't want to integrate each one of them. So what I wanted to do instead is we could just look at any one of these, and we can actually kind of just generalize it. So instead of worrying about what we have for coefficients and exponents, let's just look at an integral. We'll keep the same bounds, 0 to 2 pi. We'll just call the coefficient like a. So we're integrating a to some other value bix dx. Now, when we just integrate this doing the normal thing, we're going to end up with a over bi, and this is just going to be e to the bix. And now we'll look to evaluate it from 0 to 2 pi. Well, when we do this, we'll keep this a over bi up front. Then evaluating 2 pi, we end up with b 2 pi I. Then plugging 0 into the exponent here, e to the 0 is just going to be 1. Now, I'm not too worried about this because that's some constant value, but what is this thing right here? Well, for this, we can actually use Euler's formula that we have right here. So all we need to do to use Euler's formula is where we have x there, we're going to use b 2 pi instead. So let's see what happens. Just using this, we're going to have cosine of, I'll write this as 2 pi b, and then plus I sine of 2 pi b. Now at this point, what I notice is it's really important that b is just an integer, right? Because if b is some fraction, we don't know what this is going to be. But if b is an integer, any integer multiple of 2 pi, we know how to evaluate that. So sine of any multiple of 2 pi, or any multiple of pi even, that's going to 0. So this part of it goes away. But cosine of 2 pi b is just as easy. Any multiple of 2 pi for cosine, that's going to be 1. So what just happened is this term here is going to be 1 as well. So we end up with 1 minus 1, which is just 0. So multiplying it out, we just get 0. So what that tells me is this generic integral right here is always going to be 0, regardless of these constants. Doesn't matter what a is, doesn't matter what we're multiplying times 0, it's still 0. So that means this term's going to be 0, but they're all going to be 0. And so if all this is 0, then we can just say our integral is 0. And like I said, we've really generalized it. This exponent could be something very different. But now one quick note on this exponent does need to be odd, because if it was even, when you do this thing, this part right here, when we expanded it out, in the binomial expansion, if this exponent was even, in the binomial expansion, you'd have one term in the middle where the e's cancel out completely and you just have some constant value. Let's just call it c right here. So if this exponent was even, this c value is still going to be easy to calculate. It's going to integrate to like c times x. It's just not going to be 0, so it's something you need to be aware of, that this only works when the exponent's odd. Okay, interesting alternative method. Not necessarily a quick way, but just a good way to use the complex definition of cosine. So we'll stop it there. Thanks everyone for watching. Have a great day.